Assalamu alaikum everyone and welcome to this video lecture. My name is Mahir Fayaz Onon and today we are going to explore one of the most important topics in embedded systems, timer programming in 8051 microcontroller. Specifically focusing on mode 1, which is the 16-bit timer mode. By the end of this video, we will learn what timers are, why they are used, how to configure them using registers like tmod, THO and TLO, and how mode 1 actually works inside the chip, and finally we'll look at a complete example program that generates a square wave using timer 0 in mode 1. So let's get started. First, let's understand what a timer really is. A timer in the 8051 is basically an internal hardware counter that increments automatically with every machine cycle. Think of it as a stopwatch that built right into the microcontroller. Once you start it, it keeps counting up on its own without any help from the CPU. Now, why do you need timers? There are four main reasons. First, generating accurate time delays. For example, when you want an LED to blink every half second, or when you want a uh, delay for a specific amount of time before sending data. Second, counting external events. When used as a counter, it can count pulses coming in on an external pin, useful for things like counting how many times a door opens. Third, generating baud rates for serial communication, essential when you are transmitting data to a computer. And fourth, producing square waves or periodic interrupts, useful in sound generation, motor control, and similar applications. Now, here's the most important concept. The timer gets its clock from the crystal oscillator, but divided by 12. So, if you are using a 12 megahertz crystal, the machine cycle frequency becomes 12 megahertz divided by 12, which equals to 1 megahertz. That means the timer increments every 1 microsecond. It's the foundation of every delay calculation we will do later. Now let's look at what's inside the 8051. The 8051 microcontroller has two 16-bit timers called timer 0 and timer 1. Both are identical in functionality. So whatever we learn about timer 0 applies to timer 1 as well. Now here's an interesting point. Even though each timer is 16 bits wide, the 8051 is a 8-bit microcontroller, meaning its registers can only hold 8 bits at a time. So how do we handle a 16-bit timer? The answer is simple. Each timer is split into 2 bits registers. Timer 0 is accessed as THO, which holds the high byte, and TLO, which holds the low byte. Similarly, timer 1 has TH1 and TL1. When combined, THO and TLO together forms one 16-bit counter. The same goes for TH1 and TL1. So when we load a value, you actually load it into two separate 8-bit registers, but internally they work as one. Let me walk you through the block diagram so you can visualize what's happening inside. On the left, we have the crystal oscillator connected externally to the chip. Let's say is 12 megahertz. This signal goes into a divide by 12 circuit, which brings the frequency down to the machine cycle rate 1 megahertz in this case. This 1 megahertz signal is the clock that drives the 16-bit timer registers made up of THO and TLO. Every time this clock ticks, the timer increments by 1. Now, controlling this whole operation, we have two important registers. The tmod register decides which mode the timer operates in. The TCON register is used to start and stop the timer, and it also holds the overflow flag called TFO for timer 0. When the timer counts all the way up to its maximum value FFFF in hexadecimal, and then it rolls back to 0, the TFO flag automatically becomes 1. This flag is our signal that tells us that the delay is over. Now let's quickly look at the special function registers or SFRs that we need for timer programming. There are 5 of them. TMOD at registers 89H is the timer mode register. It selects the mode and decides whether the timer behaves as a timer or a counter. TCON as in address 88H is the timer control register. It contains the start stop bit and the overflow flag. THO and TLO are the high and low bytes of timer 0 at addresses 8C hex and 8A hex. And TH1 and TL1 are the high and low bytes of timer 1. Out of these, two most crucial ones you must understand thoroughly are TMOD and TCON. Let's focus on TMOD now. The TMOD registers is 8 bits wide, and here's the interesting thing about it: it splits exactly in the middle. The upper 4 bytes from D7 to D4 controls timer 1, and lower 4 bits from D3 to D0 controls timer 0. Within each group of 4 bytes, we have 4 fields: gate, CT, M1, and M0. Let's understand each one. Gate, this decides how the timer is started. When gate is 0, the timer starts through software. We simply set a bit in the code. When gate is 1, the timer only runs if an external pin into 0 or into 1 is also high. For most applications, we keep gate is equal to 0. CT, this stands for counter or timer. When it's 0, the device acts as a timer, counting machine cycles from the internal clock. When it's 1, it acts as a counter, counting pulses from an external pin. Since we want a timer, we set this to 0. M1 and M0, these two bits together select the mode. There are 4 possible combinations. When M1 and M0 are both 0, we get mode 0. When M1 0 and M0 is 1, we get mode 1. When M1 is 1 and M0 is 0, we get mode 2. And when both are 1, we get mode 3. This is called the split timer mode, which we rarely used. So for our purpose, we need M1 equal to 0 and M0 is equal to 1. Now let's actually build the TMOD value for timer 0 in mode 1. We want gate is equal to 0, CT is equal to 0, M1 is equal to 0, and M0 is equal to 1. That gives us a lower nibble of the 0001. Since we are not using timer 1, we leave the upper 4 bits as 0000. So the full TMOD value becomes 00000001, which in hexadecimal is 01H. In assembly, the instruction is move TMOD #01H. This single instruction configures timer 0 to run in mode 1 as in software control timer. Just for reference, if you want timer 1 in mode 1 instead, you will load 10H in TMOD because now the mode bits are in the upper nibble. Now comes the heart of the topic: how does mode 1 actually work? Here's the mechanism. Let's go step by step. First, THO and TLO together form a 16-bit register. This register can count from 000H all the way up to FFFH. That's 0 up to 65535 in decimal. Secondly, we don't let it start at 0. Instead, we load an initial value into the THO and TLO. This value that's calculated based on the delay we need. We'll see how the calculation in a moment. Third, we will set the TRO bit to 1, which is short for time run for timer 0. The timer begins incrementing every machine cycle. If our machine cycle is 1 microsecond, the count goes up by 1 every 1 microsecond. Fourth, the counter keeps going up all the way it reaches FFFF. On the very next tick, it rolls over, meaning it wraps around back to 0000. At the exact moment, the TFO flag becomes 1 automatically. This is the overflow event, and it tells us the delay has completed. Now, here's a very important limitation. Unlike mode 2, mode 1 does not auto reload. After the overflow happens, THO and TLO are both 0. So if we want the delay to repeat, we need to manually reload the initial value ourselves. Now let me give you a clean 6-step procedure for programming timer 0 in mode 1. Now let's see a code about it. Here we are loading the T-mode registers with 01H. This tells the 8051 that a timer 0 should run in mode 1 as a software control timer. Load THO with the high byte of the calculated initial count. Then we are loading TLO with the low byte of that count. Then we are starting the timer but setting TRO is equal to 1. From this moment on, the timer is counting. Then we are keep monitoring the TFO flag. As long as it's 0, the timer is still running. When it's become 1, the overflow has happened and our delay is complete. Then we are going to clear the TRO to stop the timer, and also we will clear the TFO to reset the flag, and if the delay must repeat, we will reload the THO and the TLO and go back to the loop. Now let's see a problem statement. We want to generate a square wave in pin 1.0 with a half period of 50 millisecond. That means pin 1.0 will be high for 50 millisecond, then low for 50 millisecond, and then high again, and it will run continuously. Let me walk you through the assembly code. We will start with the directive org000h, which tells the assembler that our program begins at memory address 0. Then our first instruction, mob tmod hash 01h, it configures timer 0 in mode 1. Now we enter a label called back. Then we will go into the loop, and here we load our THO with 3C hex and TLO with B0 hex. These are our pre-calculated values for 50 milliseconds. Next we will use the instruction CPL P1.0. Here we are complementing. Means it flips the state of a pin P1.0. If it was high, it becomes low, and vice versa. This is how we will generate the square wave. Then we call a subroutine called delay using a call delay. After the delay completes, we go back to our main loop, which is the back, using sjump back, and the whole thing repeats forever. Now we are setting the timer using the set b tr0. Here we setting the timer to 0. Then we are using a loop. Here the jnb tfo comma wait means that jnb means jump if not bit. It keeps jumping back to the wait level as long as tfo is 0. The moment tfo becomes 1, which happens when the timer overflows, the loop exists. Then we're going to stop the timer using the clear tro, and we'll clear the overflow flag. Then finally use return to go back to the subroutine. So that's it, a complete working program to generate a 10 Hz square wave in pin 1.0. So in the main function, we just toggle the pin and call the delay inside an infinite while loop. Before we wrap up, let me mention three important limitations of Mod 1. First, there are no auto reload. After every overflow, we must manually reload THO and TLO. This takes a few CPU cycles and introduces a small timing error if we are not careful. Second, the maximum single delay is limited about 65.5 milliseconds when using a 12 megahertz crystal. For longer delays, we have to call the delay subroutine multiple times in a loop. Third, our example uses polling. The CPU keeps checking TFO in a tight loop, which wastes CPU time. In the real applications, we use interrupt instead, so the CPU can do other work while the timer runs in the background. So we can say mode 1 is perfect for delays up to 65 milliseconds, making it ideal for things like blinking LEDs, generating audio tones, or creating precise timing signals. That brings us to the end of this lecture. I hope this gave you a good understanding of timer programming in mode 1 of 8051. Thank you for watching. Assalamu alaikum.